Hello, so let's try to install MicMap on a new workstation where we just have the plain OS installed, in our case CentOS 8, and basically not much else. So we want to try and get MicMap running on this machine. So what I suggest is going to the GitHub repository of MicMap, which is open here in this browser. Go in the releases section and get the MicMap container, which contains the software already pre-installed. So let's copy this link here. And then let's go into the machine itself, switching here to the shell here. Let's create a temporary directory for the purpose of our tests. And let's retrieve zip file. Okay, so missing wget. Yes. Try again. Okay. Let's just see. Yeah, I have plenty of room. Here, so now we need singularity to run it, which is probably not here, so that is another thing we need to get. Okay. So let's go back to the browser. I have prepared in this example.md file a few simple command setup for, well, at the beginning there's some explanation how the singularity container was set up first. We can skip this. Well, this is the piece here I just performed. Another bit we will need is the reference data that goes with the MicMap, so the data basically to describe the, for example, in this case, the human genome reference. It's pretty large, so make sure your workstation have enough space. So let's copy this and go back here. switching, pasting the command here, so that will take a little while. The next thing we will need on the workstation is to have the hugepage set up, because the MicMap software uses hugepages from the kernel, and the way it is set up by default, for example in CentOS, doesn't work for our purposes, so we need to adjust these kernel parameters. So here I'll just copy them and we will need to set them up on the workstation itself. So this needs to be added here. So meanwhile the download of the tarball completed. So let's see. We can now unpack this. Okay, so let's see again. So let's try again. There, better. Okay. So here, it's still going. Takes quite a while. Let's see. This is done. So we can remove the tarball, make some room. And here we use 127 gigabytes. Okay. So now I'm afraid we need to reboot the machine to make sure the transparent hugepage thing is installed. Another thing I will need is this the huge admin command. So Let's do this one as well. Yes. Okay. Let's reboot. Takes a few minutes to reboot. Okay, so this is what we will need next. Let's see if things are back. So here, let's see. Okay. So far, so good. This looks okay as well, and this is now never, which is fine as well. So let's try to mount this. Sounds even correct. So now that's nice. So here in the other screen we can start then singularity. Let's to make sure we are not interrupted in the middle of something. Let's run, for example, Tmax missing. I prefer to set it up like screen. Okay, so we have the Tmax going, so we can now try to test if things are working properly. So let's go back to the browser view, and in the browser we need to go into the singularity container. So let's copy this thing. Launch it since I want to use my TMP demo directory. Let's just add it here as well. Okay, so we are here. So let's now go back to the browser and use this very simple example of too small fastq file. Copy the first one, paste, and second read of the fastq, copy, paste here. Oops, forgot to switch, so I did the paste here, as you can see, and I now have those two files. Same length, so that's good. Let's go back in the browser view. So this is just to clean up two things. So copy just to make sure we have no leftovers. Okay. Yeah. We are good. So now we need to put the reference data into the huge page file system, so that if we go back in the browser view, that is what this command here will do. It will load the reference data from the file here and put it in the huge page file system. So copy this command, switch view, paste here, and go. Takes a little while. Okay, and if we repeat the ls above, we now see we have files there. So an h. So these are the file sizes expected: 4 gigabytes for the first two, 32 gigabytes for the next, and 1 gigabyte for the last two files. Okay, now we can run actually the MicMap software itself to do the mapping. So let's copy the whole line. Go back there. And so we specify that the reference files are now in the huge page file system. That's the -g and -p parameters. And then we specify a few other parameters to decide how many threads and things like that. You can look it up in the simple documentation. and then the two fastq files with -1, -2, and the results will be put in TMP demo with a tst_b38 file start. So let's run, should go pretty quickly. Okay, and now still there, and we see the output of MicMap. So a log file with _log, and then files with the beginning as we specified, _a because we didn't use too many threads to write, but there can be _a, b, and c or more depending how things are set. And then the mapping themselves, those that are good maps directly in the chromosome, those that are chimeric with a C, capital C, those reads that are half mapped with HM, and those that are unmapped with the UM header. Now go back to the things in the browser. So if we move back to the left. But anyway, so that we checked, we can look inside each of those files with the GTL decompress command. For example, if we want to see all the perfect matches, we can use the first one. So let's just try this one to have an idea what's in there. So the output is in the SAM format, and we see the expected SAM output and just the reads that were perfectly mapped. So there was just one in the short example I provided above. We can do this with perfect, with the reads with mismatch, read with indels, etc. That's the various other commands you can see in the browser here, all these commands. Now we will sort all these things because, as I said, the MicMap itself can generate several files depending on how many threads you put, so you then want to collect and sort of combine all these things. So that's what this store compress command does. It can also do snip calling. In this case we will not want it to do calling because it's just a few read, doesn't make much sense, so we specify this -d to don't do the calling. Sorry, -c. -t is to delete the starting file once the sorting is done. So copy here, again, paste there. It runs. So of course, if you have a large amount of data, that can take a while. And in the end, you should see this line here that says that counts in both unsorted and sorted match, and it tells you how many reads we had, which if we do this word count, we have 28 lines in each fastq, and since each entry is 4 lines length, so 7 times 4 is 28, so we didn't lose any sequence. You can always check this way. Now that things are sorted, you can see that we now have this output directory where told the command to put the results. The originating files are gone, as I specified to delete them, and in the directory itself we have then files per chromosomes and per type of reads. So reads with which are perfect match have the underscore P. Those that have mismatches have M. Those that have mismatches but the mismatch is just an N in the read or underscore N. Sometimes it's happening when the machine, the sequencing machine had one problem with one particular step of the reads. Sometimes all the reads have the N at the same position, so we decided to classify them this way. And underscore G is for gapped reads. So those are those that have unique exact match on one chromosome. These are the unmapped, the half-mapped again, and the chimeric reads where one part of the read maps. They are not in a proper paired orientation as expected by the Illumina protocol in this case, for paired reads. And the last thing I wanted to show in that case was how you can visualize with these SAM tools add view. So from the browser we can copy this command here, which I have set up to show the region where the reads were originating from. So copy here, go there, paste, and so here we see on the top part is, you would have, of course, here it just have one read, so the coverage is pretty insignificant, but you would see a sort of pile-up of the reads to give you an idea how much coverage there is in this genomic region. So that here is the sequence on the reference genome, that's chromosome 21, these are the positions, and then these are the reads. So reads, there is one pair per line, and when there are right pointing arrows, it means this is the read 1 on the positive strand, and read 2 here on the, or the other read on the negative strand. That's what you expect for Illumina reads. We can navigate, so going left we can see. So the top one is the perfect read, which has a perfect match. There is no mismatches. The one right below, there was an N at this position, so you see here with this difference. If we go further, so there was also an N here on the other read of the pair. If we go a bit further right, we will see the read which had a single mismatch, so C in this case, and the read here and another different C here. That's just the way I constructed those reads. You can also see in the top coverage that you have a bit of red to indicate there was a mismatch in this position. Each nucleotide has one color, so C's are red, A's are cyan, I think, and etc. So you can have an idea what's the difference. And I think if we go a bit further right, yeah, we hit the read which had the indel, so this underscore means there was a deletion at this position, and well, there was no change on the other part of the read. You can look at the quality score if you type the Q letter on the keyboard. Here I just made the map so they are all the same. But that's if you want to check what's the quality when you see go back to the read with the mismatch here. If you want to check what was the quality value of the snip, you can do it here. And if you hit H, you have a sort of help menu to tell you what are the different commands available in this view mode. And to quit is capital Q. Okay, so we have MicMap going on this new workstation. I hope this video is useful. Feel free to get in touch in the comments or in the GitHub page if you have problems or questions. See you. Well, talk later. Anyway, have a good day. Bye-bye.